so I can post this afterwards. Thank you everybody for letting me know you're here. As usual, I'm going to be assuming you have looked at the worksheet already. When I posted yesterday, no, it was a little later than usual, sorry. But I did post it and I let you guys know. So I don't know how far he got in lecture today. I'm hoping he at least got to the beginning of SN1 reactions, but I don't know. You can let me know if something is something you haven't seen. Yes, okay, good. So you covered like what nucleophiles are good for SN2 and leaving groups and all that jazz, I'm assuming, if you ended up getting to SN1. So we should be comfortable with most of this, I think. If there's anything that looks completely like you've never seen it before, then that's fine. But I mean, we'll get there when we get there. I'll just start strolling. I'm probably not going to be able to fit everything on this page. I'll try. It should be okay. Thank you. Okay. So this question is just asking if these substrates will be good for SN1 or SN2 reactions. So I guess I'll just point out which one I want you guys to tell me what it is, and then we'll go over why. So first, this one, would this be good for SN1 or SN2 reactions? Top left circled. Do we know how to determine that? It's okay if the answer is no. You guys can let me know and I'll explain, and then the rest of them will probably make a lot of sense. Okay. Yeah, this is good for SN2, so I'll put that in here. The way you determine if something's good for SN1 or SN2 is like you have to think about the mechanism, and for SN2, it is a backside attack, so like nucleophile hydroxide is a good example. It will come from the back and attack the carbon here attached to the halide. And it specifically attacks from the back. It can't attack from like the side where the halide is. So a transition state that he might have drawn or shown you is like this. And the dashed lines are showing that the bonds are partially broken and partially formed. So the hydroxide, you can see it's coming from the opposite side from the chlorine. And I'm telling you all of this because it's important. So this carbon here with the halogen on it, it's a primary carbon. It's only bonded to one other carbon. And primary carbons are good for SN2 reactions because like the more substituents are on a carbon, the harder it is for something to come attack from the back. Because like, I don't know, say this is a methyl group and this is a methyl group and this is a hydrogen, then this would be a secondary carbon, and it would have been kind of difficult for the hydroxide to attack here because like a methyl group is a relatively large thing, so like they probably would have kind of blocked the hydroxide from coming in. So I know that's a lot, but if you don't want to remember every little detail, you can just remember that SN2 is good with primary and secondary positions, but the mechanism, the backside attack, explains why that's the case. That's kind of messy, so I'm just gonna get rid of it. Okay, so I guess we'll put this here. And then how about this substrate? I already kind of gave it away, but yeah, SN1 because SN2 is good for primary and secondary. Did he show you the mechanism for SN1 reactions? I think I went over it on Tuesday, but hopefully he went over it. No, maybe not. I don't know how far he got, but I can show it with this quickly. Either way, the SN1 reaction, the leaving group, the bromine here, just leaves. The nucleophile doesn't end up attacking when it leaves. So carbocation forms. And hopefully you recall that the more substituted a cation is, the more stable it is. So if it's on a tertiary position, it's going to be more stable than a secondary, which would be more stable than a primary. So if you have a primary leaving group, then it's pretty much always going to be SN2. And if you have a tertiary leaving group, it's pretty much always going to be SN1 because a primary cation is not very stable, so it would never want to do SN1. And a tertiary position is nearly impossible to attack from the back with a nucleophile, so it's never going to want to do SN2. So that's why, like, if it's one of the extremes, it's going to be exclusively one or the other. If there are any questions, please stop me because this chapter is kind of important. But otherwise, like usual, we'll assume we're all on the same page. Okay, so what about this? Can this be SN1, SN2, or both? Good first step is looking at the alkyl halide here and determining if it's primary, secondary, or tertiary. And it's secondary because the carbon with the halogen on it is bonded to two carbons. So I wrote like what SN2 and SN1 substrates are good with. And you can see there's overlap. If it's secondary, it can be either or. And that is the answer. This one just depends. So I assume he went over like what solvents are good for SN2 reactions today and leaving groups and nucleophiles and all that. So depending on what solvent and nucleophile you used would determine what reaction happens with a secondary. And we'll cover that when we get there. Don't worry about it. Thank you for coming. So I'm still going over number one. Okay, I don't know if I ever got a definite answer. Did he cover solvents and leaving groups and such? Because if not, okay, that's good. So I can cover that when I get there. Whoa, stop that. Sorry, the chat box is being weird. Okay. What do you guys think of this one? So the halogen is on a secondary carbon because this carbon is bonded to two other carbons. So do you think it'll be SN1, SN2, or it will depend? Well, I'm not getting an answer, but I would think that an initial guess based on the last one would be it depends because it's secondary and the overlap. But an important detail with this is the leaving group is right next to this is basically a terpene group, I guess I would call it. It's right next to a quaternary carbon. That's another thing you can point out. It's right next to a quaternary carbon. So this is a really bulky thing. It's kind of in the way, and in order to attack from the back, nucleophile would have to come here, but like there's a carbon here and a carbon here that would kind of jut out and make that a little difficult to do. So because of this quaternary carbon right next to the leaving group, that makes it difficult to attack from the back. So this would be SN1 primarily, because the backside attack is difficult to do. And what about this substrate? So the carbon here with the leaving group is primary because it's only bonded to this carbon here. So will that be SN1, SN2, or it'll depend? Yep, SN2. So hopefully this isn't too cluttered. You know, that was a lot, but you kind of have to know a lot of details for these, and it gets easier with practice. Okay, number 2 is pretty much the same as number 1. That's not a great way of doing that. Okay. So the question here is just which of these is good for SN2, and there can be multiple right answers. So let's start with this. Would this be good for an SN2 reaction? It would not, because the carbon there is tertiary. So like it's much easier to see with this. It would be pretty much impossible for the hydroxide or anything to attack and break the bond from the back. So yeah, tertiary is not good for SN2. What about this? Yeah, it would be good for SN2 because this carbon here is only primary. It's only bonded to one other carbon. And this carbon right next to it isn't quaternary, it's tertiary, so it's not hindering the backside attack too much. What about this one? So yes, this halogen is primary. It looks like there's some conflicting answers. So like, yes, it's primary, so it looks like it's good for SN2, but this is similar to that part from question 1. The leaving group is right next to a quaternary carbon with like 3 other branches besides to the leaving group. So because of that, it'll be kind of difficult to attack this from the back. So it is not good for SN2. So look at the surroundings to the leaving group when you're trying to figure it out. It's pretty rare that this exact circumstance comes up, to be honest. I don't think it came up for me in my class, but it's still good to be aware that this quaternary center can make the reaction not happen, SN2. Okay, what about this one? This carbon is primary, so yes, it is. It's only going to be hindered if it's the quaternary center right next to it. This is just tertiary, so like unless you see something that looks like this right next to the leaving group, you don't have to consider the surroundings. Just look at the carbon attached to the leaving group. You know, that's kind of an annoying rule, but it is what it is. OChem sucks sometimes, to be honest. Okay. I've already been using the lingo a lot, so this will probably be semi-obvious, but we'll still go over it. Kind of ran out of space. That's a CN over there. Try to squeeze it in. Okay, so can you guys just type in the chat what the leaving group is and what the nucleophile is, I guess? If you can recognize it. Yeah, O tosylate is a leaving group. And I hope he covered this. It's the best leaving group for these reactions. So if you see this, then that's a leaving group and it's going to be very fast. And then cyanide is the nucleophile. And this K here, it's only a counterion because this by itself has a negative charge, I believe it's on the carbon. And then the potassium has a positive charge, so it counters the negative charge to make this more stable. So this is just like you seeing sodium hydroxide, because hydroxide has a negative charge and sodium has a positive charge. So if you see sodium or potassium in the spot up here above the arrow, and that's usually where the reagent that reacts with the leaving group is. But if you see one of these, then that means the other thing has a negative charge. And that's important because negative nucleophiles are better for SN2 reactions. So this would be an SN2 reaction. Just sort of skipping ahead, but it is. Okay. Still on number 3. So what would be the leaving group here and what will be the nucleophile? This problem gets a bit redundant. That's why there's not too many parts to it. So we can see chlorine is gone in the products. And halogens are a good leaving group along with O-tosylate, so that will be the leaving group. And water acts as nucleophile here. You don't have water in the product, but I could show the mechanism if you guys want, but it is the thing that attacks. So water is nucleophile. And if you ever want me to show you a mechanism for something and I don't, feel free to say something and I'll go back. But I mean, it's a typical SN1 reaction. So just, you want it, I'll show it, but otherwise I'm moving on. Okay, I'll go back. Okay, so that's fine. I tried waiting, but I didn't wait long enough. So this is an SN1 reaction, and pretty much everything about it backs up that it would be SN1. The leaving group is on a tertiary carbon, so that means that the cation will be stabilized when we get there. And I don't know how far he got for SN1 conditions, but the nucleophile should either be like acidic or neutral. And the solvent should be polar protic. So for SN2, the nucleophile should be a strong base. It should have a negative charge usually, which is what we saw in the first part with potassium cyanide. The CN had a negative charge, so it was a good nucleophile for that. This water is like, it can act as an acid or a base, so it's fine in terms of like the acidic. And then polar protic just means like it's polar, like it has a dipole, which water does, and protic means it has a hydrogen attached to something. Like basically just hydrogen bonding is a possibility, and you should remember from Gen Chem that water has hydrogen bonding. Anything that has hydrogen attached to a oxygen or something else like that would be polar protic. Sorry, I'm jumbling the words, but like this, acetic acid would be another polar protic. And there are some others like methanol and ethanol that are common. So those are the conditions, and I'm just pointing out that everything is good for SN1. In terms of the mechanism, the first step for SN1 is literally just a leaving group leaving. If it's a OH, it has to kind of be coerced to leave by adding a proton, but with a halogen, it kind of just leaves. So we get a positive charge. Then the water attacks, positive charge. And now the water has a positive charge, so it's not very happy. We also don't have the product, but when the chlorine left, it had a negative charge, so it can come and take a proton from the water. So hydrochloric acid forms as a byproduct. And all SN1 reactions follow these same steps. Leaving group leaves either just by itself, or if it's OH, it gets a proton and then it leaves, and then the nucleophile attacks a cation and product. It's just different leaving group and different nucleophile, but the mechanisms all look the same. So, yeah. Okay, last part for number 3. So this question is a bit redundant, so I'll just go ahead and say like the thing that leaves, like you don't see it in the product, it's kind of obvious, it's the leaving group. And the thing that gets added, in this case, it's a SH or a file. That's the functional group for that. It would be this. And again, the sodium is acting as a counterion because just like hydroxide, this has a negative charge. So yeah, just this question is relatively simple. I've spent a lot of time on it, so I'm moving on. All right. Sorry, I'm doing this as fast as I can. The last one was SN2, if you're talking about number free. And just like with, I'm not gonna, actually I can draw it down here again to go over it quickly. So like I pointed out, well, first, it's secondary, so it could be both SN1 or SN2. It depends on the conditions. And for SN2, the nucleophile, like I said, should be basic or neutral. So basic would be like a good nucleophile, and a good nucleophile has a negative charge because it wants to use that negative charge to attack something. So you don't see the negative charge up here, but because of the sodium, you should know that there's a negative charge there because the sodium's just balancing it. So this is a good nucleophile. It's a good basic nucleophile, so it's good for SN2. And then the solvent is generally supposed to be polar aprotic. So it's a polar solvent, but it doesn't have hydrogens on places where it can do hydrogen bonding. And DMF is a polar aprotic solvent. I think it's called dimethyl formamide. I might have mixed it up with something else, but I don't remember what it looks like off the top of my head, but it's polar and it doesn't have hydrogens on like oxygen, so it's aprotic. So it's a good solvent for SN2. Yeah, these get easier with practice. And when we get to the question about solvents, I guess I'll look up pictures of the solvents to draw them. You don't have to memorize them, but I'll do it just so you can see them. Okay, I'll just leave that there. Oh, that's not what I'm looking at. I ran out of space. Okay, so for number 4, I'm asking to rank the rate of the reaction for an SN2 reaction with the following substrates. So we know for SN2, it's generally better for primary and secondary positions. So that's a good place to start. Like primary is the absolute best and secondary is okay, depending on context. All right, so like this is primary, and I'll just go ahead and label them all. This one is secondary because it's bonded to 2 other carbons. This is bonded to 3 other carbons, it's tertiary. And this one is primary because it's only bonded to 1 carbon. So both the top left and the bottom right are primary, but there is a difference between them. Which one is going to be faster? Bottom right or top left? Yeah, bottom right. So primary is fastest. This is going to be 1. This one is slower than the other one because it's right next to a quaternary carbon. It's right next to this carbon with a bunch of different substituents that kind of take up a lot of space, so that will slow down a reaction. And that will slow it down so much that even though this is primary, like I pointed out, this isn't a good spot for an SN2 reaction, so the secondary leaving group will be better. And then this likely won't do an SN2 reaction, but if it did, it would be faster than the tertiary position because the tertiary position is like nearly impossible to attack from the back. This just makes it more difficult, but not necessarily impossible, I guess. Still wouldn't want to do it, but generally want to do it with a primary or secondary because that's faster. And that kind of ranking of reactivity and rates is something that should be good to do. So it's like primary is faster than secondary, which is faster than being next to the quaternary carbon, and then tertiary is the slowest. That doesn't look great, I'm sorry. Okay, so first, before doing the mechanism, you should figure out what kind of reaction it is, because the mechanisms, yeah, but I'll go ahead and write that. Like if you thought it was SN1, then you drew the mechanism like that, then that would be wrong because that wasn't the exact path it took. This is SN2. The first thing to look at is the leaving group, like the substrate. It's secondary, so it could be SN1 or SN2. We have to look at the reagents. If it was primary, we'd know it's SN2 straight off the bat, or if it was tertiary, it would be SN1, but it depends here. Hydroxide has a negative charge that's countered by the positive charge, so negative nucleophile, that's good for SN2. DMF, like I pointed out a few minutes ago, is a polar aprotic solvent, so again, that's good for SN2, so all of this is pointing towards this being an SN2 reaction. And on top of that, I did give you the product, and a thing to note about SN2 reactions is the product inverts stereochemistry. So it went from being a dash to being a wedge. This went from being S to being R. So it inverted stereochemistry. And it does that because of the mechanism that I'll go over. So SN2 is a backside attack. So the nucleophile attacks from the back like this. And I'm going to draw this, but it's not an intermediate. It's not like a carbocation. This is a transition state. So it's something we can't like isolate, but it kind of helps explain the inversion here. That's why I'm drawing it. And I drew it at the beginning today too. So I know I kind of turned this molecule just because it's easier to draw this like this. This carbon here is like trigonal planar, so these three things on the dash wedge and the line are kind of in the same plane, and then the hydroxide's coming from the opposite side of the bromine. So because it came from the back, and I'm labeling this as a transition state, but because the hydroxide attacked from the back, it flips the stereochemistry, so it goes from the dash to the wedge. And you should know that this happens, that it flips stereochemistry. I don't think I have a question on this. Actually, I might have. I do, never mind, I'll get to that later. Okay, so I'm not going to write that down, but for number 6, it's a true-false question. And it says the 2 in SN2 means that the reaction goes through 2 steps and passes through an intermediate. Is that what the 2 in SN2 stands for? And is that statement about the reaction true? Yeah, so this is false. The 2 in SN2, it has to do with the rate of the reaction. You have some constant, and then the rate for the reaction depends on both the substrate with the leaving group and the nucleophile. It depends on 2 things. So it's SN2 means like nucleophilic, that's the N. Substitution. And then it's bisubstrate. That's what the 2 stands for, or crap. I know it's like bi or di or something, like the 2 has to do with this here. It depends on 2 things as opposed to depending on 1 thing. I'm sorry, I don't remember all the little details, but it's like, I honestly don't remember, but I think it's like bi something. That's what the 2 is for. And it doesn't go through 2 steps, and it doesn't go through bimolecular. Thank you. So it's bimolecular nucleophilic substitution. That's what SN2 stands for. And then SN1 is just unimolecular. Because for that, it only depends on the substrate or the leaving group. And that has to do with the mechanism, which we'll just do quickly. Like, I know this is going beyond the question, but I think it's useful. Like, the only slow step for this reaction is getting the chlorine to leave, but once it leaves, the nucleophile can attack this pretty quickly because it doesn't want to stay positive. So the rate only depends on how fast that leaves, and that depends on the concentration. So you don't have to know all these little details, but you should know that like SN2 doesn't pass through 2 steps like I said it did. And I could see him wording the question similarly to that. So that's just something to take note of, I suppose. Okay, I'm gonna move on. Okay, so these are different nucleophiles that could be used. Like if we were reacting something, it would be whatever goes on the top. That's generally where the reagent or nucleophile goes. So this is ethanol. And would it be good for an SN1 or an SN2 reaction as a nucleophile? So I will, since it seems like we don't know, I'll go ahead and put this again. It's generally like it's either positive or acidic, or it could be neutral. I'm gonna move the HBr to give myself more space. And then SN2 would be negative / basic. These two kind of go hand in hand generally, or neutral. So ethanol is neutral. and it can act as an acid or base, so I guess that does make it a bit confusing to some extent. But I had a question earlier, number 3, where I went over the mechanism where we added water, and water could also act as an acid or base, and it ended up doing an SN1 reaction. So like the fact that this hydrogen is here is very similar to comparing sodium hydroxide to water. There's a negative charge. Well, that also kind of goes with this, yes, but for this question, these are all nucleophiles. They're not the solvents we're looking at. So ethanol is also a solvent generally, but we're looking at it as it would act as a nucleophile. So this is the thing that would attack like a cation here if a cation formed, or it would do an SN2 reaction and attack like here. It seems like you guys don't know, so I'll go ahead and say it's SN1. It's similar to what I was talking about with number 3 with water. Water is not a good nucleophile for an SN2 reaction because it's not a very strong base, and this also isn't a very strong base. So I guess like you should look more to the neutral for SN1, and then SN2, like if it's basic, it's generally going to be SN2, but if it's not negative or basic, then I feel like it's more likely to do SN1. That's usually how it seems to go. You know, that's not a great rule, but kind of just is what it is sometimes. Yeah, there's a chart of these. You can memorize that if you want. I never did personally. I just try to remember these rules. That's what I'm trying to get. That's what I'm trying to convey here. But the chart works too. Okay, so that's SN1, and there's the hydrogen there that kind of helps figure that out. What about this one? This is an alkoxide with a negative charge on the oxygen. Would it be good for SN1 or SN2? So the negative charge is something I pointed out for SN2. So this is good for SN2. If you ever see a negative nucleophile, you should just immediately think the negative charge makes it a not necessarily good, but like strong nucleophile, I guess. And stronger nucleophiles are better for SN2 than SN1, because for SN1 it doesn't really matter since it's just attacking a positive charge. It's pretty easy to attack a positive charge. That's another thing you can remember. Okay, what about this? This is an acetylide anion. And just like with the last parts, there's a negative charge. This time it's on a carbon. So it's going to be SN2. And you hopefully recall that we've seen this before. It was possibly on your exam. This is something you'd react with like an alkyl halide to form your carbon-carbon bond. And now you know that it did an SN2 reaction to do that, so you know the mechanism for it. You'd be able to draw it if it came up. Okay, what about sodium hydroxide? I already kind of highlighted the trick for this, I guess. The negative charge is not given to you when you're shown sodium hydroxide, but, whoa, okay. But yeah, thank you. The sodium is acting as a counter-ion to stabilize the negative charge on the hydroxide, so the fact that there's a negative charge makes it good for SN2. That's not how I wanted to do that. And what about hydrobromic acid? Will that be SN1 or SN2? Yeah, this will be SN1 because hydrobromic acid is in the name, and acids are generally better for SN1 than SN2. So HBr or HCl are good for SN1 reactions. If there are no questions, then you guys are either very confused or you're understanding. Again, if you have questions, please stop me, but like we're gonna go over these multiple times over multiple worksheets probably. So it should hopefully get easier. Okay, so the propane at the bottom is the same for all of these. So basically when we're talking about how good leaving groups are, we're looking at like when the thing attached to that middle carbon leaves. So I'll just show them all as if they were SN1, although it might not necessarily always be like that, but I'm just gonna show it. So like we'd end up with a hydroxide ion here, a negative OTOS here. This is just a CH3 here, so this is what would result from it. This is called an alkoxide ion. And then a chlorine anion. So when you're trying to figure out if something's a good leaving group or not, there's a chart that displays like how good those leaving groups are compared to each other. You can memorize that, that works, or you can think about like how good these things are at stabilizing negative charges, like how happy are they to be negative, are they going to be reactive? So like it's kind of hard to remember with everything. I don't remember the structure of OTOS, but it's probably a super weak base because this is the best leaving group. That's just something I memorized, to be honest with you. OTOS is a good leaving group. It's the best one. A chlorine, chlorines are halogens, and they only want one electron to be like an noble gas. That's something from Gen Chem. So when they have a negative charge, they're actually extremely happy. They're not very reactive. I mean, they can still react, but they're generally pretty happy. So because of that, that makes halogens good leaving groups. But a hydroxide, on the other hand, is a pretty strong base. Like you might recall from Gen Chem, sodium hydroxide and potassium hydroxide were some of the strong bases that you had to memorize, I think in Chem 1A. And the hydroxide is the basic part of it. So because it's a strong base, it's not going to be very happy staying the way it is. It's going to want to react with something. And if it's reactive, then like, I don't know, I'll just redraw that. Like, you get the positive charge after the hydroxide leaves, but instead of having the nucleophile that you want to attack the cation to form a new product, it might just go back because it's so reactive, it's not going to want to stay gone, so you're not going to get a new product. So that's what makes it bad, because it doesn't stay gone, it comes back pretty quickly. And it's the same case with alkoxide anion. They're pretty strong bases. So that's not something you had to memorize, but they are relatively strong. So that's just something to know. Like there's nothing stabilizing this negative charge. So it's a bad leaving group. So you can either use the reasoning I just did or memorize which ones are good and which ones are bad. And mainly halogens and OTOS are like the good ones. And then bad is pretty much everything else, if you want to look at it that way. This is solvents. Okay, yeah, this works. So you hopefully recall that I've pointed out a couple times SN1 is generally good with polar protic. Oh, that's the top of the screen. And SN2 is good with polar aprotic solvents. So the difference is like having a hydrogen on an electronegative atom like oxygen or nitrogen would make it protic, and then not having hydrogen on one like that would make it aprotic. So starting with MEOH, this is just methanol. Is this polar protic or polar aprotic? So it has a hydrogen bonded to this oxygen here. So because of that, it's protic. Yeah, I'm gonna abbreviate polar protic as PP, and I'll abbreviate polar aprotic as PAP, just to save myself some time. Which atoms are the ones that matter again? For hydrogen bonding, if that's what you're asking, it's generally, why were we like that? Oxygen, nitrogen, and fluorine, I'm pretty sure. Those are the three that mainly come up because those are some of the most electronegative. And you're generally only going to see oxygen and nitrogen because fluorine's not very good in organic molecules. And primarily oxygen in terms of solvents, to be honest with you. Okay, so methanol is a polar protic solvent because the hydrogen is attached to oxygen, so that makes it a protic solvent. And because it's polar protic, it's gonna be a better solvent for SN1. You could still do an SN2 reaction in methanol, but they would probably have to be a primary leaving group. So yeah, just like the solvent doesn't necessarily lock in what reaction it's going to be, but it influences the reasoning behind it. And I'm not going to go over the reasoning too much today because I don't have a lot of time, but probably covered it in lecture. I thought that protic is SN2. No, polar aprotic is good for SN2. It should be in the lecture notes. I know the reasoning behind it. It takes a decent amount of time to explain. So I can do it next time if you like. But in terms of just memorizing, if you don't want to know why polar protic is good for SN1 and aprotic is good for SN2, oh, okay. It's all good. Okay, so DMF is, I believe, dimethylformamide. No, look it up. Is that a polar protic or polar aprotic solvent? Yeah, I was worried about that. I'll go ahead and draw it, actually. It's a hydrogen. So is this polar protic or polar aprotic based on this structure here? Aprotic, yeah. You don't have to memorize this structure, so please don't actually. I'm just showing it to you so you can see what it looks like. So this is polar aprotic because there's no hydrogens on any oxygens or nitrogens. And because it's aprotic, it's better for SN2. What about ethanol? Is it protic or aprotic? It's very similar to methanol. So it's actually, I'll go ahead and just say it like it's pretty easy to see the similarity. There's a hydrogen on the oxygen just like with methanol, so it's SN1. This is formic acid. Actually, I'm kind of surprised I took that. But it looks like this. It's pretty unstable, to be honest. I don't think it would ever be used as a solvent, but in the event it was, would this be polar protic or polar aprotic? Yeah, it's protic because this hydrogen is bonded to the oxygen here, so there's hydrogen bonding. So it's polar protic, and it's good for SN1. I don't remember what HMPP is. Draw it so you can see it. So it's hexamethyl phosphoryl, phosphoramide, okay. So is this polar protic or polar aprotic based on the structure here? Just like with DMF, the oxygen doesn't have any hydrogens on it, and the nitrogen doesn't have any hydrogens on it, so it's going to be aprotic. And aprotic is good for SN2. That's fine. I understand why people wouldn't want to answer. This is a lot of info. This is acetone. You should know that eventually. You don't necessarily have to memorize that by now, but acetone is very common, so you should know what it looks like by the end of OChem. Is this aprotic or protic? Well, like all of these carbonyls, the oxygen doesn't have a hydrogen on it and the carbons don't, so because of that, it's going to be aprotic. And that would be good for SN2. Water, hopefully you know that water can do hydrogen bonding, and there's a hydrogen attached to an oxygen. There's actually two, so it's protic. Protic's good for SN1. DMSO. Dimethyl sulfoxide. So that's pretty easy. Just looks like this. Just like DMF and the HMPA. The oxygen does not have any hydrogens on it, so it's polar aprotic. That's good for SN2. So, like I said, you don't have to memorize the structures for DMSO, HMPA, and DMF. But I showed it to you so you can see like why they're aprotic. In terms of memorizing these, like methanol is just an abbreviated, well, MEOH is an abbreviated way of saying methanol, but hopefully you recognize it because it's come up in the past. And you should be able to see the hydrogen on the oxygen that makes it protic. Same with ethanol and water. And if you're using an acidic solvent, then that would be protic. And then acetone, hopefully you can remember what it looks like. But then the other the common aprotic solvents are the ones that I have here, DMF, HMPA, and DMSO. And those are all abbreviations for really long names. So if you just remember the solvents with weird abbreviations, then those are the aprotic ones. That's what I did when I took the class. That's my recommendation. Yeah, that's really the only tip I have there, besides memorizing the structures. Just remember the abbreviated ones are aprotic. The only other common aprotic solvent, because it's pretty good, is acetonitrile. And that's just this. It can be written like this as well. So they could put acetonitrile or MECN or CH3CN. All of these could be written like on the bottom of the arrow to show that that's the solvent. And this is aprotic because there's no hydrogen on this nitrogen. So it's polar aprotic. And that would be good for SN2. So that's the only other thing I'd recommend remembering if you want to just memorize solvents. Have I covered anything that he didn't so far? I hope I'm not getting ahead of him because I would imagine that's confusing. Okay. That's good. Okay, so when we're determining what the product should be, it's good to figure out what the leaving group is, what the nucleophile is, what kind of reaction it's going to do, and all that stuff. So leaving group is the halogen here. What will be the nucleophile? Also, I'm going to go ahead and point out this is a secondary position. Yeah, OET, the alkoxide, is going to act as the nucleophile. It has a negative charge. That doesn't look great. But the oxygen has a negative charge. It wasn't given to you, but like I said, the sodium has a positive charge that cancels it out to kind of stabilize it. So we have a negative nucleophile that's going to be a strong base. So that's something to keep in mind because it's secondary. It could be SN1 or SN2. but we have a strong base, and we also have acetonitrile as our solvent. What kind of solvent is acetonitrile? Protic or aprotic? Anybody can answer if they know, but this again. It's okay. Aprotic, yeah. This is being weird. So yes, it's aprotic. And like I pointed out, the base is a strong base, so the nucleophile and the solvent are both pointing towards this being SN2, because strong nucleophile and aprotic solvent are both conditions that favor an SN2 reaction. So we know that like the chlorine's going to leave and the OET is going to attach. But what's going to happen to the stereochemistry? Is it going to stay the same? Is it going to be a wedge, or is it going to change? Well, because it's an SN2 mechanism, you remember that the nucleophile specifically attacks from the back, right? So because it attacks from the back, that leads to an inversion of stereochemistry. So it goes from being a wedge to a dash. And the stereochemistry of the product is extremely important. If you just drew this, like, you'd be partially correct because you figured out what the nucleophile was and it's substituted. But the stereochemistry inverting is the main characteristic of an SN2 reaction, so you have to make sure you show that you recognize that. Or if it was a multiple choice question, you'd have to pick one where it changed or something along those lines. Okay, so again, we have a secondary position, so it could either be an SN1 or an SN2 reaction. This nucleophile is very similar to what we had before. Instead of an F oxide, we have a methoxide anion. It's negative, it's a good nucleophile. What about this solvent? Is it protic or aprotic? Yeah, it can be a bit confusing, but okay, so like, I don't know if you're, yes, okay, so I don't know if your professor covered this or if he will have a question like this on the test, but I think I'm gonna give you a sort of graphic, not graphic, but like, so what I mean by this is like, first, if you're trying to figure out if something is SN1 or SN2, you look at the substrate. If it's primary, it's pretty much always going to be SN2. It's tertiary, it's pretty much always going to be SN1, regardless of whatever's over here. It's probably going to be one or the other, depending on primary or tertiary. If it's secondary, like it is here, you can't figure it out based on the substrate. So the next most important thing, figuring out if it's SN1 or SN2, is what kind of nucleophile it is. If it's a strong nucleophile, that's going to be good for an SN2 reaction. So that's going to favor an SN2 reaction. If it was a weak nucleophile or an acid like water or ethanol, then it would favor an SN1. If you can't really tell, then you'd look at the solvent, but usually you can tell just by looking at the nucleophile. So what I'm saying is, like, look at the nucleophile that you're using, and the solvent might contradict what kind of reaction it's going to do, but that's okay because it's just a solvent. It doesn't stop the reaction. It just isn't the best for your reaction. So based on what I just told you and the fact that this is a strong base, is this going to be an SN1 or an SN2 reaction? Yes. Good. Yep. Again, I don't know if he's going to go into this much detail where he gives you a contradictory solvent, but in the event he does, look at the nucleophile, ignore the solvent. So because it's SN2, the stereochemistry is going to invert. So we get a wedge instead of the dash we started with. Okay, I only have 3 minutes, so I'm going to go over this next one relatively quickly because I want to get to the last one. That one is a bit important. Okay, so again, we have a secondary position. It could be SN1 or SN2. We have a strong nucleophile because it's negative, and DMSO is polar aprotic. It's one of the things with a weird abbreviation, so that will help you remember that it's aprotic. So everything is pointing towards this being SN2. But because I didn't give you the stereochemistry in the reagent or the reactant, like, you can't determine what the opposite stereochemistry is because you don't know what it is here. And that's partially because this isn't a chiral sensor, but I also just didn't give it to you. So you can't, like, don't go from a reactant with no chirality shown to drawing something like this just because it's SN2, because that would be technically incorrect. So just draw it with a regular line if you're not given stereochemistry. If you are given stereochemistry and it's SN2, flip it, but otherwise just don't worry about it. This problem is, okay, again, secondary leaving group position, so it could be one or the other. The nucleophile here is ethanol. That's what's on the top of the arrow. So is that a good nucleophile or a weak nucleophile? The oxygen here has lone pairs, so it can act as a nucleophile with those, but there's no negative charge, so it's not a super strong base, like what we've seen in the last few parts. So I'll go ahead and put weak nucleophile. And then we have water as our solvent. Is that polar protic or polar aprotic? So protic, yeah, because it's water. Hydrogen bonding is very much a thing with water. So weaker nucleophile, like, or neutral acidic nucleophile and polar protic solvent, those are both factors that are better for an SN1 reaction. So this is going to do an SN1 reaction. And in terms of the mechanism, I'm going to show it because it's kind of important. So the bromine leaves, you get this cation here. What is the hybridization of a carbocation? Do you guys remember that? It came up with alkenes. When we were looking at intermediates, the hybridization is going to be the same. If the answer is no, that's fine. Not SP, but it's not SP free, so it's the one in the middle. Yeah, it's going to be SP2. And what's the geometry of an SP2 carbon? Yep, so it's trigonal planar. Well, I'm gonna draw it more flat than that. So you can think of this as kind of being flat. And the positive charge is like where the p orbital is, which is above and below the plane. So because it's a flat species, the nucleophile can either attack from the top or the bottom. It doesn't care which side it attacks from because both are equally easy to access for the most part. So because of that, it's going to lead to a mixture of the two enantiomers, because like if you attack from the top, say you'd form a wedge, and if you attack from the bottom, you'd get a dash. And if you form an equal mixture of the two, then you form a racemic mixture, which isn't chiral. So all of that is a fancy way of saying you lose the chirality when you do an SN1 reaction because it can attack from the top and the bottom because the intermediate is a cation. So when the oxygen attacks, and then the bromine's going to take the hydrogen. I'm just going to show that here so I can get to the product because I know I kind of went over the time. In a way you can show that there's no chirality anymore. I don't know if you showed this, but I like to call this a spaghetti bond, or you can just call it a squiggly line. But when you have a spaghetti bond like this, you're showing that there's like an equal mixture of the two enantiomers. So it doesn't matter which one you have because you have both. So there's no chirality. So SN1 leads to a loss of chirality. If you started with it. If you didn't have it to begin with, then it doesn't matter. But if you have a dash here, you get a squiggle here. And water can also act as a nucleophile. So even though it's the solvent, it can technically also attack. So if you wanted to be completely correct with this, you'd probably end up with this as well. You get both of these as products. But I doubt he'd give you something like this where both can act as nucleophiles and solvents at the same time, because that's a little weird to wrap your head around. Okay, I'm sorry I went like 10 minutes over, but hopefully everything made sense to some extent. This chapter is a bit tricky at first. It gets easier over time. I hope this was helpful. And I'll see you guys next Tuesday. Thank you. I'm glad it was helpful. Have a good day, everybody. Go ahead and stop the recording.